Starting, yeah.
Eu quero giros. Só preciso escrever alguma coisa.
Vê se tens lá fora. Não tem um quadro aí fora. Eu costumava ter.
Era
À
este.
esquerda, à esquerda. Ah, era este. É.
Era este.
Olha ali a caixa deles. Esta televisão.
Está aqui, Miguel. Está aqui. Está aí.
Eu acho que sim.
Está bem. Pronto. Ok. Está bem. Pronto.
Vais gastar.
Deixa eu estar aí.
E é do antigo.
4. Tens de ter coisa.
Como é que assim?
E é do antigo, pá.
Que é formado, assim, aqui, né? Não é da porta.
Eu não fiz depois.
É da porta.
Por acaso, não sei. Há alguma regra do orientador sentar à direita do...
São leves, ele é que manda. Não é o presidente.
Então nós somos quantos lugares? 4?
Sim, é uma cadeira.
Não, são dois.
A videoconferência.
10. São 3.
São 3. Estou indo.
Que é cool.
Tudo bom?
Acho que é público, bem?
Então. Já deixa-me lá. Vai ver. Quando eu disse.
Estás bom?
Eu já falei com ele. Lembrou-se há 10 minutos, há meia hora, mas agora não sei se lembra. Aí eu não quero ver.
Também é só subir. Vais lá acima.
Sim, vou lá dizer, professor. Vamos.
Eu vou lá acima e vamos para
Porque tem que ser lá em cima, não pode ficar embaixo.
Tenho uma aí. Eu não tenho. Ah, obrigado. Então,
Tem preferência, ponha.
não tenho preferência, então uma que seja daquelas preto ou vermelho. Vermelho não. Preto ou azul. Então pode ser uma também, pode ser uma qualquer.
Você conseguiste pôr?
Sim, não sei. Eu não consigo comentar isto. Eu supposed to put air conditioning here. No. This was somewhere here is like hell.
Então, se é
Aspirador.
They kind of made.
But this was the air conditioning of the old ones because it was centralized and everyone would get the same air independently of the size of the room.
Done.
I could not switch.
Well, I tried to play my part, man.
Acho que isso não tem.
Olá!
Não,
Olá, força. Sentai. Agora.
estás a ver?
Ana também vai, não vai? Ana não sei.
Então, disseste tudo.
Yeah, sure.
Então, você está.
Mobile, switch off. I go to the math, man. Otherwise, I know someone will call me.
Some for business partners from
Well, what are you doing now? What are you doing? Make photos, no?
Yeah.
Still make photos? Good.
Trying to work in that probably with the market that is.
Right, this is good. Maybe can go around the world. Some nice photos
I'm
for
going to, after this, I'm going to Thailand.
That's good.
Thailand, be careful, it's military.
Oh, no. Well, maybe you can become a journalist.
But they have military crew. It's 5 years. It's almost like elections there. So.
I went in Egypt.
During the coup.
No, well, actually, it was the best trip I ever had because no one was there. And I can visit all the monuments.
Yes, precisely.
Nothing in Cairo. I don't think that was right. I went to Luxor and Aswan and met all the rivers.
When was that?
In April. This year, yeah.
And still
Eu moro perto da biblioteca.
Same as can be, you are the only person there. Even if someone tried to do you like, it's a very poor investment. That's the only way. Going to club. What's that guy now? What's everything.
Because we're discussing
No, Cairo is very dangerous.
you cannot go to this country anymore.
Actually, I tell you, if you go to look for it's the best time you can go. Because when you have all this, this market starts with the stuff. Yeah, okay. By the way, I think I'm very competent. But it's something very the place is amazing. I went to Abusin now. Abusin now, it's kind of they move in during the fog. You probably know when you see right around from the Nile and then so it's dann das wird you got to go something. Come on, I'm sorry. You have drugs?
Costa Rica não.
No.
Costa Rica somebody told me yesterday.
Pronto. Não me estás a ver, pois não? Quando começares a ver, avisa. Ui, então estás com quase 1 minuto de atraso.
Não tive da Suíça?
Já foi há muito tempo. Que existência! Não é que isto
Isso
não está a
é
fazer. Não, acho que são importantes.
Several hours from Nebraska but no, it's unstable.
No, and I was right actually. When I went go, because I like no, I went for hours and I was like like 6 persons on the cruise. Used to be 120.
But
No, you can just do it. And the price was very low. That's why I like to
I mean through the agents.
No, I went.
Didn't buy the tickets.
No, I went there because I organized myself. I buy the tickets. Yeah. But actually, yeah, you go there. I knew that I could do that, and then actually everything is organized with the plane. No, I decided not to. Not even to that. Gary, but always, as I said, he said, you should avoid the place here, thank you. It's very sad, you should avoid this. Yeah. Okay, well, that's not my case. I went to Woodstock.
But there was a direct flight to Luxor.
Yeah. Oh, I'm flying from London.
Okay.
Sorry? Part of the world? Well, and then from there, I picked up the boat and went down there. But it's like the moment. It really blew me away. Culturally, because normally I have tendency to see the Greeks and the Greeks are very good. Actually, I realized they have. Well, the Egyptians were much younger than us, and they are really amazing.
So
Hello.
It's really very good. And when it's normal, it's not that good because it's party people. Really, the food they installed for almost a year. They have been too busy. But no, everyone, no one's good there. And they have like 100, I have like 800 cruises, and they have like 200 working just to keep the sun alive. Really great stuff.
Professor said that he was in the meeting.
Yeah, I know.
Eu tenho que ir.
Já ganhaste.
Yeah. Então fiz falar.
Não precisa, eu vou fazer.
Razoavelmente.
5, 10 e 15. Como eu disse.
Não sei, pá, tem que ver a minha agenda.
Está muito calor aqui.
Não há por cima da janela qualquer. Não. Não, só pode estar o membro do. Só pode estar o membro do governador.
É?
Vamos ver.
Então acho que podemos fazer o seminário em português, você já é fluente. No? No? Not yet. So we have to resort to English. So we start the proofs, as provas de mestrado of the candidate and Miguel Cunhal, Henriques, and Miguel has now 20 minutes exact on the clock to give his seminar, and then we have some time to make questions. So now it's 3:10 in my clock, 3:12, so we can start.
So first of all, good afternoon. I'm here to present my thesis that consisted on the study of the nearby type-1a supernova, SEN 2008-Q. So type-1a supernova originates when a white dwarf suffers a thermonuclear disruption that happens when it reaches a mass of about 1.4 solar masses. This is done by accreting stellar matter either from a red giant or from another white dwarf. Well, in order to distinguish this type of supernova, type 1a, from other supernovae, you need to look at the spectrum. If the supernova doesn't present any hydrogen absorption lines and presents silicon lines, thus it's considered to be a type 1a supernova. The light curves were found to be powered only by the radioactive decay of the nickel-56. This was found by Arnett in '82. As we can see, the light curves do not overlap exactly, but Phillips in '93 found out that there is a relationship between the width after 15 days and the maximum brightness, the maximum magnitude. So the brighter supernova have the decline of the magnitude is slower than the less brighter supernova, which decline faster. So if we consider this, and we can see this here in this relationship, if we consider this, we can calibrate the light curve magnitude in order to be much more overlapping. So this allows us to standardize the magnitude of the supernovas. This is very, very important because having a very bright event that can be easily identified by the spectra and has a consistent brightness, this allows it to be used as standard candles that can help us to measure distance either very close or very far if we measure the flux, the incoming flux, and we know, as I said, the flux that is emitted from the supernova. This was done by Fraunhofer, and it was awarded the Nobel Prize for this. He plotted the redshift against the effective magnitude of the supernova, and he found out that opposite to what it was expected, there were some supernovas that were slightly less bright than it was expected. So this meant that the universe seemed to be accelerating its expansion instead of decelerating as it was expected. Now, about the supernova with which I worked, 2008 Cube. It was found in the constellation of Pisces in around here, NGC 524, which is this galaxy. This galaxy also had an event, also another supernova, type 1a, the 2-year one, in 2002. So the field stars were already calibrated by the author of that paper. This is the supernova, and as we can see, it's far from the center, so no stray light is to be expected to affect the measurement. And also, the field is not very crowded, and this will help in photometry. The observations were performed in 2 telescopes, Asiago and NOT. Asiago in Italy, NOT in the Canary Islands. Both have AFOS cameras. NOT also uses a Mosca camera, and they both possess standard UV-VRI filters. In order to do photometry with the images, they need to be corrected. So, in order to obtain the final corrected image, this one, we need, with the raw image, the uncorrected image, this raw image needs to be subtracted the bias, which is basically a zero exposure of the sensor that allows us to know the noise introduced by electronics in the sensor and the constant that shifts slightly the measurement. Also, dividing it and subtracted by the bias, we have the flat. The flat is a photograph of an evenly illuminated region of the sky, or from a dome, for instance, and allows us to see what kind of artifacts are introduced in the image by defects on the filter, for instance, or dirt in the sensor or dirt in the mirror. Bias nowadays are very low. The noise is very low, so it's very easy to subtract. It's basically a constant. But as I'll show you, flats can be very important to be used. As you can see, this was one of the images I worked with, and this is the original image, and this is the flat. As you can see, there is actually a structure introduced by the filter. This is the U filter. After performing the corrections, we end up with this image, which is the corrected image and the one that will have photometry done. As I said before, the field is not crowded, so we can use aperture photometry. If it was crowded, we would have to use another kind of photometry that would allow us to select carefully the star we wanted to measure. So always aperture photometry done. We have the object, and around the object, we introduce, as the name says, an aperture. This aperture has a certain radius, and the radius is defined. I chose the radius to be of 2 full width of measure because it has around 90% of the total signal detected and has the best signal-to-noise ratio we can have. If we chose to increase the radius, what we'll be doing is catching a little bit more of the signal, but much more noise. So the signal-to-noise ratio would actually be worse. So this is the aperture, and around it, in gray, it's the annulus. In this annulus, we average the measures inside, and it's far enough from the star so that the wings of the star that will affect this measurement are not detected. And in here, we detect the background from, for instance, moonlight or from the galaxy, etc. And we subtract these measurements, this average, to the measurement done inside the aperture. This is the field we use the standard stars, and for each of these stars, and also for the supernova, aperture photometry was performed, and each of them, for the 29 nights of observations, for the 5 filters per observation, were unfortunately manually marked in order to be possible to do the photometry. After the photometry was performed, the standard stars were used to determine in the transformation equation, which is an equation that allows us to transform from our set of filters that, even though are fabricated to be standard, they are not perfectly standard, they are transformed to a standard filter, defined as standard, and thus enable us to compare, to use different telescopes in the same study of the object, or even comparing different objects among themselves with the same standard. So, be instrumental is the magnitude we measure with the aperture photometry. This standard is the standard magnitude that, in the case of the standard stars, has already been determined. In here, this is the air mass and the extinction. This is the color term, which is constant for a certain telescope with a certain filter and a certain camera. So if no changes in the hardware are performed, this value will remain constant throughout the whole observation. These are also standard values of magnitude for the standard stars. The secondary extinction, again, the air mass. So we have all the values except the 0 point for the standard stars. So we determine the 0 point for the standard stars for each filter, and within the filter for the different stars, we average the 0 points in order to have the 0, because 0 points should be the same inside the same image, the same filter in the same day. So we average them in order to have the 0 point for that image for that filter. So we do this to all the days, and we end up with a list of 0 points. Now, we could also use this equation for the supernova, but the problem is this part, the part that is color dependent, doesn't really work with supernovas because they are not stellar objects. Their spectra is different. So this is an empirical relation, and in order to not have this error introduced, we need to use what is called the S corrections. The S corrections are basically a generalization of this part here. So in the S corrections, we need to know the spectra of the star. We need to know the system response of the filter, the standard filter, we need to know the system response of our set of filters and the air mass of the Earth. So using this, we can compute the correction for the supernovas. So how do we do this? We convert this into the natural system, compute the correction and sum the correction to the magnitude in the natural system. After correcting it, I fitted the white curve template for a type 1a supernova, and I found the stretch, which basically indicates the amount of compressing or dilation in the time frame that you will need to do to fit correctly my supernova with the template. So I determined the stretch to be 0.859, and the stretch for a perfectly normal supernova is 1, as expected. It's a little bit different, but still within the parameters to be a core normal type 1a supernova. Also of interest, in the peak magnitudes, we can see the B and the V magnitudes are very close to each other. Their difference is very small. This indicates us that the supernova didn't suffer from old galaxy extinction. So no dust between us, in the galaxy of the supernova, between us and our observations. These observations, by the way, are corrected for the Milky Way extinction. Now, comparing these results with results of other authors, I found them to be consistent. But some differences appear. For instance, with Milne, that uses different sets of filters that are non-standard, we can see that even though the B and the V are consistent with mine, here, this one is not that consistent. And this comes from the different system response of the filter. Comparing the color indexes with the other authors, and also with the Type 1a core normal supernova 2003 DU, which has a stretch of 1, we found that B minus V, V minus R, and V minus I have the expected behavior. Why? Well, it seems that they grow faster after maximum, and they are redder in all the bands I told. Well, this is to be expected because the stretch in this supernova in 2008 Q is smaller than in the supernova 2003 DU. The big difference appears in the U minus V. In the U minus V, you can see that clearly it's different. Why is it different? Well, Milne, which was and 2008 Q, sorry, are indicated by black dots. Milne, which was the author of the paper with the U-God photometry, wrote in his paper that the 2008 Q seems to be a UV bright supernova. What does this mean? Well, a UV bright supernova is a supernova that before maximum, the U filter is brighter than in the core normal supernova. So we can see in his photometry, clearly that it's brighter. My photometry is slightly dimmer than Milne's photometry, probably because the S correction doesn't work that well in UV bright supernovas. So, in fact, the S correction is overcorrecting the supernova. Also comparing with that database of type 1a supernovas with delta M15, which is equivalent, more or less, to the stretch parameter, we find that the curves are actually very similar to each other. And in fact, there are 2 or 3 curves that are almost equal to the 2008 Q. The spectra that I used to also classify or sub-classify the supernova as a core normal was reduced by Valery Stanichev and was given to me. And already, just by looking and comparing this OAQ, comparing it with other spectras of type 1a core normal supernovas, the spectrums are very similar. So, in principle, they will be 2008 Q again is a core normal. But let's look at a little bit further. I analyzed the 2 absorption lines of silicon at 6,100 and around 5,700 and something. And I measured the equivalent width, which basically gives us the broadness of the light, of the absorption line, and I measured the velocity, the expansion velocity of the silicon line, of this one. So using the branch classification that uses both equivalent widths of the silicon lines, we find that 2008Q stands right in the middle of the core normal supernova, thus confirming again that this is a core normal supernova. Going to the Wang classification, where the velocity is plotted against the equivalent width of the rightmost silicon line, we see that clearly this supernova is not a high velocity silicon supernova. The 91BG and 91T are peculiar supernovas, and we already know from the photometry that photometrically it's a normal supernova. So this overlap here does not concern this analysis. And also looking to the velocity against with the time change of the velocity, we see that plotting against other core normal supernovas, the velocity works as changes as expected. So again, core normal supernova, even analyzing the spectrum. Well, concluding, the purpose was to analyze and sub-classify the supernova 2008Q. I reduced 29 days of observations and analyzed them, concluding that the stretch of 0.859 needed to be applied to this light curve, and indicates that it's a photometrically normal supernova. Also, comparing with the data from other authors for this supernova and the data from other supernovas with a similar delta F15, I found that the results I obtained were consistent. Also, it didn't suffer, because of the B-V color, it didn't suffer any extinction in the host galaxy. And spectroscopically, both Wang and branch subclassifications classify the supernova as a core normal supernova. And also, the velocity line evolves as expected. These observations are, till now, the best sample data for 2008Q, and it will be published in the hope that they will integrate a larger set of supernovae, thus contributing for other analysis in cosmology, for instance. And that's all. Thank you very much.
Thank you. Now, so it's now 3:31, so we took 90 minutes.
Well, so I can try to use one more to make it 20.
Which is fine, within the hours. So now we have some time to questions and answers. And I start with Professor Emilio Lopes from Évora University, and also invited professor here at the Physics Department, EST. So please.
Okay. Well, first of all, I should start with a few comments that I would myself and congratulate you and to providing for the nice work, because it's quite complementary to the general term, which means you go in the job of optical astronomy and that analysis, optical photometry and spectroscopy, and it's quite a large and ensemble, which is very nice for thesis like that, because we really understand the basics of optical photometry and spectroscopy. And also it's very nice that we managed to go from the beginning to the end with a goal and achieve the goal, and finally, not really an expert, but I understood all the steps was properly done, and master all the steps were quite complex and significant. And again, it's with knowledge that might be the work, the agenda, which we consider. But I'm supposed to ask you some questions, and I will ask some questions to make it a little more funny. Not be an expert may help a little bit myself. And one of the things is that you, for instance, probably you said it, I think you said it in the thesis, and that's interesting to remark. How can you, in terms of evolution, what the mechanism you have to go to one type of supernova?
from one level to another.
Yes, I mean, in terms of, I know you have in terms, yeah, exactly. Yeah. Well, you have the correct, you know I lost it.
So in terms of evolution, all the stars start in a nebula.
Yeah.
And the smaller stars, like our sun, evolve to a red giant. And after the nucleus is made only from carbon and oxygen, the star isn't big enough for its temperature in the nucleus to be able to fuse carbon and oxygen. So in the red giant phase, the atmosphere is already expanded and they just continue expanding. And the nucleus stands around in the white dwarf. So this is the white dwarf that it's going to originate eventually in the right conditions a type of a supernova. So the other kinds of supernova come from the large stars that evolve to supergiants, and these supergiants are able to fuse till the iron element. And after the iron, the star stops fusing and goes into a catastrophic collapse, exploding, and giving rise to a supernova. Depending on how the star evolved, if, for instance, it was the outer parts of the atmosphere of hydrogen and helium, we might have a type 1C or type 1B supernova.
Related our the main point is because you are looking back in time,
yes,
and imagine the composition of your universe is not different. We expect that to be the 1 million question we are looking at. We expect slightly evolution from different surfaces to oh yeah, sorry. Okay. If you look back in terms of evolution, you'd expect some kind, but I guess the kind of worries you have when you study kind of like this,
yes.
What kind of caveat or what kind of problems you should expect or don't expect in terms of using this as the reference?
Type 1A.
Yeah.
Well, if we look very away, they will be still, even though they are very bright, if you look far away, they will start to be less and less brighter, and they might be very difficult to identify.
You expect the light curve to change slightly? Like
they will change because of the redshift. So the redshift will actually change the light curve, and in this case, it was a nearby supernova, so the K correction, that's how it's called, that accounts for the change in frequency of the light in order to have with the filters. It didn't have to be applied, but for IZ supernova, we need to perform a K correction that takes into account the shift in frequency and doesn't cover of the light of the supernova.
Can you probably you talk about the stretching of the very important parameter?
Yes.
Is it easy to explain in simple terms physically what this can be as a kind of qualitative image rather than just the? I mean, the observers make reference to it. You basically manage to.
Yes. If you imagine, this is this is 2003 DU, and stretch is let's imagine that this one is the template, and we have another light curve and we try to fit the template. And in order to fit the template, we pick up the time basis and we stretch it or compress it to try to adapt mainly for this particular on maximum. So if it's wider, the light curve we have, we need to compress the template. Well, the opposite. Sorry, if it's wider, we need to compress the light curve, our light curve, to fit it to the template, and the opposite.
Just a quick question, because we talk about point spread functions.
Yes.
Your point spread function is in your calibration process. Is very different from a Gaussian, or I have no idea. Just maybe very simple ones.
Well, they can, as I wrote in the thesis, they can be fitted with a Gaussian.
Yeah,
there is also modified Lorentzian, and but no, they are just a three-dimensional Gaussian.
They are not very different in terms of form.
No, well, if the seeing is good, they won't go very far from the seeing is all stable is the atmosphere, and if there are no clouds, no dirt in the atmosphere, etc. And if it's stable, it should be a Gaussian.
That's you mentioned already. You can have some correction maybe with dust and the reddening.
Yes, the extinction.
Could be. I mean, if just for periodic, if you don't correct that, is the curve very also?
It might be redder.
Okay.
It might be the bluer parts might have a slightly lower intensity than they would have if they weren't corrected, because dust reddens the light.
Well, as I said, I don't need to make much more questions. I've done another final and this now is this final point is you calculate the sort of velocities of some certain time. Can you have an idea of velocities and then can you have an idea about the dynamics, what is going on in terms of the supernova and in terms of velocity or this?
So the expansion, and as we can see, even taking into account the measurement of the other supernova, the expansion starts very fast, and then it starts to slowly, starts very fast, and then reaches gets almost constant, and keeps expanding almost constantly. As you can see, it starts very fast.
And they are all over, include your supernova.
Yeah, well, me and 4 other authors.
Okay, but Thank you.
Thank you.
Okay, that was quick. We expected 30 minutes question time.
Well,
we got 10 minutes.
You have the time. You have the rest of the time.
No, I'm not supposed to make questions because I'm the president, so and I'm not the expert. So, so now we can ask the co-supervisor, because the supervisor is not here for some reason or another, but I also don't understand very well. But anyway, then we can ask the co-supervisor to make...
The decision direction of the IST, just one supervisor can be...
Yes, but the supervisor, is the supervisor. So now we can ask the other member of the committee to make questions.
Well, I'm not going to make questions because I'm really familiar with the work that is done, but I would like to say a few words of why the work that we have been maybe try to qualify some of the parts. Well, first of all, there are many different super explosions in the universe, and many of them are very exotic, very interesting. And as a pure researcher, one may be tempted to go after those more exotic events that they specifically are feeling. And one question that might be asked, why do you study these objects that they seem to be one compared very well one to the other? They are all very simple. And the question is very simple. It is because this normal type of instrument that we can use in cosmology to actually measure distances, which measure between distances. Distances in astronomy is a very difficult task, so there is not easy. And with these precise objects, we can actually measure very precise distance across galaxies. And in turn, if we can show this Hubble diagram that is used to discover the acceleration of the universe, you can actually connect this simple physical object, which appears to be a thermonuclear explosion of a white dwarf, all with the same mass, and to transfer it to really answer some very important questions that we would like to understand, like the origin of the universe and what is its shape and what is basically the constituent of the universe. And it is all these objects that you see in this Hubble diagram, is one of the first ones that was published, are these four normal, boring, let's say, type of supernova. From the point of view of technological application, they're very important. And here comes the work of people like Miguel and studying this object, because in order to put them in this diagram, we need to understand the physical objects. And when Miguel approaches to get his master physics, that's very good task to study one of these nearby and that's we learned there. These ones particularly very difficult case because it's a very precise, so you need inclination in colors and reducible aperture photometry. And at the same time relate to a bigger picture in the watchable framework. So we thought that's a really nice task, which pleased with the work that Miguel did, very carefully. He easily understood, and he's got this unity of calibration, like the X direction, and you see come across in many different fields. So he did a very good job in this, and he also performed the analysis very carefully and determined all the important parameters that can be determined and can be used to better understand these objects. And as he said, the ultimate goal is that you study many points nearby. Right, so you can only consider their case, very example, you can do a very high quality selector. And eventually, with increasing the database with these well observed very good objects, you can actually start testing your physical models, which eventually lead to better understanding of objects. So, all in all, I say that Miguel did a very good job, getting a little bit faster, but for reasons maybe a little bit beyond control, it's not as fast, and even more plans to work on no objects, but at the end of the day we decided to go on for the object that we have complete picture. And all in all, as I said, he did a very good job. And yeah, we're very pleased with his work, and especially for the nice presentation here.
Okay, thank you very much. Well, I'm not an expert in this subject in photometry. I know about zero. I know that you like to present teacher and present astrophysics class to students and to people that know little about the subject. So I'd like to make you some general questions to know if you are on the right track. So the first question is that you talked about that the mass of a white dwarf that is going to explode is about 1.4 solar masses. Now, this mass is around the Chandrasekhar mass.
Yes.
So I'd like to know what is the difference between the Chandrasekhar mass and this mass, conceptual difference, and if you have to know of any reason why they should be equal numerically.
Well, Chandrasekhar mass is the mass after which normal white dwarf would collapse. Normal white dwarf or a narrow core, for instance, would collapse after it didn't have any support. So in the white dwarf, we have no fusion inside. So no photons, no energy are supporting the exterior layers, and thus the gravity is compressing the star, the object, in this case the white dwarf. If we surpass the Chandrasekhar mass, the degeneracy pressure that is created from the Pauli exclusion principle is
Okay, so that it's a bit confusing what you're saying. So what supports what?
The degeneracy pressure.
And what is that?
It's the force that electrons produce by not wanting to violate Pauli's exclusion principle.
Right. And so the max, this Chandrasekhar mass
is the maximum mass that they can support.
Yes. Following Chandrasekhar calculations, what is the radius of such a star?
Actually, I don't know that. You know, it depends on the element you have inside.
The element we have inside for this white dwarf, there are no
For the white dwarf.
Yes, we are talking about the white dwarf.
I don't really remember by heart, but it's small. Something.
No, it's not small, it's 0. So the calculation gives that when you go to 0 radius, then you get 1.44. That's the calculation by so something should happen. That's, and now what is the relation with, no, and now this mass that you calculated, what is there any relation with the second mass? And if yes or if no, what do you think?
What do you think?
What is this mass that you are shooting there?
This is the mass where the carbon starts fusing. And it starts, carbon starts fusing inside the star and gets temperature to rise because it's a degenerate star, it's a degenerate matter. So it doesn't change the volume. So all the energy that's produced from the carbon fusion is used to put the temperature higher, and then it's snowball, and higher temperature gets more carbon to fuel, the star ends up.
So is there any relation with the second mass?
I don't think so.
No?
No. I think not.
And so it's a coincidence that both of them have the same mass.
Close.
Eh?
They are close. Yes, I think so.
Yes, I think nobody knows.
Yes, it is.
The explosion of the white dwarf does not have anything to do with the jungle circadian in the collapse. It starts before that. It's just this around this mass, the conditions inside are right.
Yes.
They're numerically there.
Sorry, in fact, there could be even super-Cunhal supernovas in the right conditions. For instance, in this kind, supernovas could the sum of the masses could be higher than 1.4. For instance, in the highly magnetized white dwarf, the mass at which it explodes could be higher than Cunhal mass.
Right. Now, you also show the permuter plot of magnitude versus redshift. So now we are at, so you show that z equals 1, right? More or less, f to z equals 1.
Yeah.
Z equals 1, do you have any idea how old the universe was?
Well, it depends on the geometry.
No, more or less. I don't want to. I want up to billion years.
No, I actually don't. No, I actually don't know by heart how long it will be.
No. I think it's halfway. 6 billion years. I'm not sure. And the other thing is that what is the relation between the cosmological constant? Because in that plot they prove that there is a cosmological constant, essentially, or something equivalent to cosmological constant. And what is the relation of the cosmological constant with that deviation going up for high z? Exactly. Why a cosmological constant?
Well, the cosmological constant, in general terms, introduces that the vacuum manages to have some repulsion, produce some repulsion, and thus accelerate the expansion of the universe when we have enough vacuum. It starts to get, it wins to normal matter in terms of gravity. and it accelerates. And as we can see here, it starts accelerating the expansion.
No, but that's why you can see here. What is why is that connection?
So
How do you infer from this graph that there is a cosmological constant?
Well, the higher the redshift does, the farther it is, the dimmer are the supernova observed, compared to what should be observed if there is no cosmological constant. So, and after this, well, let's say here in a half, we start seeing the line deviating upwards, saying that in fact they are farther from us than we would expect. If they were along this line, which would be the expected. So
Why I don't understand why they are further.
Because the universe it's expanding faster.
No, okay. That's what I want to understand is the connection between that graph and distance. So you have effective magnitude,
yes,
apparent magnitude, as I can further. And you have redshift, okay, yeah. And you have Hubble's law.
Yes.
And now from that, why the curve going up or the curve going down, that was staying, why do you infer that there is a positive cosmological constant? You are not showing distance there. You are showing effective magnitude as a function of redshift. So I would like to tell me the connection.
So the farther a supernova is, the dimmer it appears to us. So if we know that the supernova has an absolute magnitude of x, if it appears x prime, this x prime is at a certain distance comparing to the absolute magnitude. So in redshift can be correlated to distance. So the bigger the redshift is, the dimmer does, the farther are the supernova.
Redshift is correlated to distance. So
Also to velocity. The farther an object is, according to Newton's law, the farther an object is, the faster it goes away from us.
Something very quickly, very quickly. Yes. The old one, not the latest one.
Ui!
And I know.
yeah, but there have deviations from the other one.
Yes, which means the Hubble constant is not constant. It changes. It changes with distance. And the farther we are from, the farther we look, the bigger is the velocity at which the object in question goes. It accelerates. The Hubble constant is bigger.
When they don't found organization for one outflow,
Okay, well, I think for me it's fine. So now we can proceed, and I ask the audience to go outside while we classify here cheating presentation.
Yeah.
Thanks very much.
Acabou!
Sim, tudo bem.
Se não der.
use